very nice lineup of 5 presentations, 3 shorts, 2 shorts, and 3 long. Right? Everyone pay attention. So this first speaker, Iftikhar Tanvir, and well, you probably can read better than I speak. So let's move.
So should I start now? Good afternoon, everyone. My name is Iftikhar Tanvir, and this is my talk. Before I start my presentation, I want to confess about something. Every time I want to start my presentation, I understand that I got these 2 hands. I don't know what to do with them. Should I put it in my pockets? Or I should make a cross-arm gesture? Or I should stand still? And when I finish the talk, my advisor comes by and tells me, you know what? Throughout the whole talk, what you did is just to sway your hands like this person. So these are some involuntary body movements that people do, and they are not aware about themselves. So experts of public speaking call them mannerism because those are purposeless, repetitive, and usually distracting. Mannerisms are involuntary, so if someone from the audience doesn't let the speaker know about their mannerism, they usually are not aware about them. So imagine if we can design a system that takes that job of the audience and make a public speaker aware about their body language. AutoManner is designed just to be that system. Now think about the challenges for designing such a system. People usually display a wide variety of movements, and this is not possible to make an exhaustive list of all these movements. So a supervised algorithm is impractical. And again, not all the repetitive movements are bad. Some gestures are good, which is relevant to the talk. Now, how can we make users aware about their body language without knowing the context? And also, if we make the system, how can we evaluate this? So AutoManner is designed to address all these challenges. Here is the AutoManner interface. There is a video player and a skeleton animation. In the video player, the users can see their whole talk in a fast-forward mode or in a normal mode. In the skeletal animation, shows the top common patterns of the user's body movements. The timeline shows where those patterns occurred. Now, there is an interesting part in this interface, which is the question and answer box. In this box, we ask question like, this pattern appeared meaningful to me. So what we are doing with these questions, we are priming the users to think more about the patterns of body language. And in our results section, we will see that this process makes the users much aware about themselves. Now let's see a demo. Here, you can see this person is giving a talk, and sometimes he scratches his hand. And the skeleton on the right, this is mimicking this pattern. And in the timeline, you can see where those patterns occurred. So how did we make the system? We used Kinect to capture 20 body joint locations, and all the body joints were captured in X, Y, Z coordinates, and we make a signal out of this called as mocap or motion capture signal. Now we made a mathematical model to model this data, and here the psi is, suppose the psi is a pattern that we want to extract, and the alpha are the activation instances where those patterns occurred in the video. If we take convolution of these 2 signals, we get this signal. And then for different patterns, we get multiple of these signals, which is eventually added and combined to this final output. So this is the model of the data. Now, if we get the final output signal, how can we go back and reconstruct the patterns and their corresponding activation sequence? That's the problem of this algorithm. We do it by formulating an optimization problem. In this optimization, we minimize the difference between this F and Fm, which is the model of the signal. So F is the signal that we get from the Kinect, and Fm is the corresponding model. We minimize the error between these two, but making sure that alpha is sparse. We also minimize the L1 norm of alpha to enforce the sparsity. We do this sparse constraint to make sure that the patterns are actually the original patterns, not just a combination of multiple different patterns. We solve this optimization problem by using an alternating gradient descent approach. So in this approach, we alternatively update alpha and psi, the two parameters of the model, and we update using just the gradient descent. Now, to enforce the sparsity, we use this this shrink and project function. So what it does, it gradually reduces every element of the alpha function so that it, over the iterations, it becomes sparse. Most of the elements are 0. We restart this algorithm multiple times to make sure it doesn't get stuck into the local minima. And that's how we solve this algorithm. This gives us all the common patterns that this person shows. Now, how do we evaluate this system? We are interested in 3 questions. First, how useful is the interface? How accurate is the algorithm? And does AutoManner improve body language? To answer this question, we designed a user study with 13 male participants and 14 female participants. All of the participants were native English speakers, and we also used 30 Mechanical Turk workers from USA to evaluate the patterns. Now, before I describe the study design, let me also talk a little bit about the treatment interface and the placebo interface. We designed a fake AutoManner interface that looked just like the AutoManner, but the patterns were not extracted using our algorithm. It was just some random sampling from the signal, and the window was arbitrarily placed in some other position than the one where it's actually extracted. We did this to evaluate what the algorithm adds more than just the video. So if the user watches the video versus if the user sees this additional information, how that compare. Now, in the study design, we recruited participants. They gave 3 minutes talk in our lab, and we asked them to evaluate their own talk. So they gave it, make a self-rating, and then they interacted with the AutoManner interface, and then they gave feedback on the interface. After that, they gave a second talk and repeated the process, and after the third talk, they just rated themselves, not the interaction anymore. So between the first 2 interactions, one of the interaction was with the original AutoManner interface, another one was with the placebo interface. This was counterbalanced. Now let's see the results. How useful was the interface? These are the annotations, annotated ratings from the participants about the interface. So you can see all of them were more than 5, so it was rated from 1 to 7, with higher the better. The users say like the interface made them aware of their body language, and it made them aware of at least one mannerism. These 2 are more than 6, which represents it's a very good for making them aware. Then we compared the placebo interface versus the treatment interface, and the difference between they made them aware of at least one mannerism is significant. Others are not significant. Here the correctness of timeline, this means all the mechanical Turker, these are ratings from the mechanical Turk workers. They rated each and every time instance in the timeline and evaluated whether these are correct or not. And there is a significant difference between the fake and real patterns. These are correctness of patterns. Here is also significant difference. Then improvement of skills. This means whether the users are actually improving their body language or not. This is a very tough or difficult test because they only interact with the system for 30 minutes, and we cannot just expect them to improve radically with a 30 minutes interaction. It usually requires longer motivation and longer time exposure. But still, we see some improvement. They were happy with the quality of their speech after in their last speech in comparison to their first speech, and that's statistically significant. There are other improvements, but these are not that statistically significant. In conclusion, this is the first attempt to automatically analyze mannerisms, and we used an unsupervised detection technique. The interface was designed for improving awareness, and formal evaluation with 27 public speakers were done, and the evidence on improving self-awareness is found in our experiment. Our code is available in hci.cs.rochester.edu under the AutoManner project. In future, we want to apply this algorithm on other modalities like facial expression, speech, prosody, and we want to make a Kinect game out of this. So thank you for listening to my talk.
Okay, we start beating the schedule. Amazing. So questions?
Maybe I can just ask you like this.
Yeah.
Is that okay? Yes.
Oh, yeah,
Oh,
live stream.
okay.
That's a good point. You can hear me good.
So I was wondering, it's a great technical talk, and also the evaluation is very interesting. I was wondering why at the end you just based the outcome from their self-ratings of their performance as opposed to having external viewers.
Yeah,
rate
that's a
what they-
good idea. We didn't do currently the external evaluation, but we did evaluations on mechanical Turkers. Probably that's some kind of audience opinion as well, but we didn't use any expert opinion. Yeah.
Are you planning to do
Yeah,
it?
in future we can do it.
Okay, questions, discussions? I have a question.
Yeah.
We all hear very nice invited talk today, which seems to be to somewhat related with some parts to what you're doing. How you can compare your work and the work on Elizabeth? Is there something which you're doing specifically they're not doing? Are you using different algorithms and approaches? How you put it in context?
This work is mainly a totally unsupervised algorithm, and we don't need any template of mannerisms.
Aha, so that's the difference. Okay.
Right.
Any question? There's one question. Elena. You need to go to the microphone, but I can go to you.
Thank you very much for the great talk. I'm wondering, do you have some data how many people actually have problems with mannerisms? Do you have some data when you just look at the population, maybe your
Yeah.
students and
Yeah, actually, when they rated themselves, all of them mentioned that they have some mannerisms, and the interface made them aware of it.
And experts in communication, would they agree that it's
We didn't do any expert evaluation here, but yeah, in future we can try that. So right now it's only based on user self-evaluation.
And a last question, but quick question. Okay. Do you think, so yeah, there are many situations where you have to speak, for example, a talk like this, but also you could be in a difficult social setting, job interviews, dating or whatever. Are the mannerisms for one person very similar, or is it situation dependent?
Usually it's situation dependent. Sometimes some person has a specific idiosyncrasies which they show no matter what is the situation. So yeah, it's actually both situation dependent and some are user dependent.
Okay, thank you very much.
Thank you very much.
Okay, so I guess we get into the next speaker. Next speaker. The next paper, we have really exciting educational system. So Narumol will talk, right? Pronounce his name right? We'll talk about
Desitra.
A simulator for teaching situated decision-making with dental surgery. That's a very important talk for anyone who has been to dentist. So let's listen to that. So we're running a little bit ahead of the schedule, but please try to keep to whatever it's located for you.
Okay. Okay, good afternoon, ladies and gentlemen. My name is Narumon Wanaprateep. I am PhD student from Mahidol University, Thailand. Today, I'm going to talk about Desitra, a simulator for teaching situated decision-making in dental surgery. Surgical skill training has been traditionally based on Holstedian apprenticeship, whereby students carried out a surgical task under supervision from human expert. But this training model has been strained by challenges of shortened training programs, reduced working hours for residents, and limitations of available operating room time. So the use of simulation in surgical training becomes popular. But despite the fact that 75% of important events in the operating room are related to decision making, but many works of surgical simulation have focused on training technical skill. And moreover, situation awareness is a key component of decision making. But existing tutoring systems do not sufficiently address this. So we implemented the first version of Desitra that provides an open environment for learning decision making by allowing students to carry out dental procedures and to make mistakes. And this open environment also provides perceptual cues and important information for making decisions. In order to design the system, we have to understand how to teach, how decision making is taught, and to find out the key cues required for decision making. So we carried out an observational study at the faculty at the student clinic at the Faculty of Dentistry, Thammasat University. We used the thematic analysis to find key cues for making decision and decision errors with the intervention strategies that human tutor use in teaching session of endodontic surgery. The key cues we found used for designing user interface and the intervention strategies as long as decision errors are used for designing pedagogical module. We implemented the system on the Android platform because we want for the maximal accessibility, we simulate the intraoperative environment by using Unity game engine and develop the tutor engine in the form of Android engine by using intelligent tutoring system architecture. When students interact with the system via Unity, the Unity will communicate with the tutor engine via XML action, and students' action will be sent to tutor engine to transfer to pedagogical module. The pedagogical module will make a decision whether the student action is correct or not. If it's not correct, then it will make a decision of strategies to intervene and provide the content of intervention. Let me show you an example screen of intraoperative environment of Decitra. In order to make the decision, students have to evaluate the current situation. Right now, we saw that the tool was already drilled, but the NML has been removed, but the dentine remains. So student has to provide the main access by choosing the tool type, to number, and also the details of drilling, including the depth, the entry point, and also direction. Okay, and here. Okay. Wait. Yeah. Here, students have to drag the tool, choose the identify the depth, entry point, and also direction. And then the tutor engine will make a decision and provide the intervention. So let me talk about how tutor provide the intervention. For each step of the procedure, system allows students to make mistakes not more than 3 times. If the error occurs for the first time, the tutor engine will give a guidance informing the incorrect action and effects of the action. If the second error remains, the tutor engine provide guidance and explanation in details. And if the third error occur, then the system will provide the demonstration.
Press the next button to start a tutorial mode. Select pencil. Drag pencil to the working tooth. Select draw action of pencil. Select the outline number 3 for premolar. Now, you have finished the process.
Well, Decitra is at the very preliminary stage. There are more challenges to do. Firstly, right now we focus on root canal treatment procedure. We have to cover more procedures. And the second thing is that tutor engine evaluates students' actions only, but students are different. So we need to do more personalization to provide intervention. And the content of intervention is context. The causal model to automatic generate content of intervention is needed. And finally, we have to do the evaluation of the effectiveness of the system in teaching intraoperative decision making. Thank you.
Okay, thank you very much. Now I have microphone. Questions? Line up. I expect to see a very long line here because it's an important topic.
Hi, I'm James Schaefer from UCSB. First, I want to say this work is, I think, really great. I think this is kind of going in a good direction. It seems like you haven't evaluated the system yet, but I was wondering what kind of plan you had to evaluate situation awareness as opposed to decision-making outcomes. Because I think if you can identify when students are making technical errors, that then separate that from their actual knowledge, that's kind of going to identify, you said before there was the 75% decision-making kind of impact and only a 25% technique impact. So again, the question is, how do you plan to evaluate SA in this kind of environment?
How do I plan to evaluation, right?
Yeah.
Okay.
Specifically, a situation awareness assessment.
Is a situation awareness assessment. Let me talk about what I learned from the observational study. When we do analysis to find the types of error happen in the operating room, there are about 3 types, and one of them is the type of putting an incorrect action in procedures. And right now we focus on that actions or procedures. We want to evaluate the system in terms of in that aspect, in terms of how well the system can help student in making a decision well before they go into the operating room. I mean, before they actually providing a service to the patient.
Okay, I think my question is still, there's evaluating the decision making, the actual observed decision making, and then there's assessing the situation awareness of the person during the task, so during the interaction with the tutorial or during the surgery. And do you distinguish between those in your work?
Sorry, can you speak out loud, please?
Oh, are you distinguishing between situation awareness and the decision making outcome in your work?
No.
Oh, okay, thank you.
So for your point, personalize the tutorial interaction. If you could say a little bit more about how you want to do it, because I saw in your initial architecture slide, there was no connection between the student model and the kind of feedback. So I'm assuming that you're going to try to put a little bit more of a connection there. So for instance, if you're going to be looking at things like affective states or cognitive load, because those are things that could impair decision making, and you might want to take into account if you want to support the decision making process.
Yeah, that's a very good point. At this moment, the system focus on the actions only,
Right.
and because students in my aspect right now, students has different background. I mean, academic background, and sometimes students needs a different types of feedback, and the affection may be very useful for the students, because for students who are sensitive, they don't want a kind of strong intervention like direction or something. So for the student that has strong background, they have more confidence, and just a little bit guidance, that'll be okay for them. This is why the personalization is needed to make it more effective for the system, and yeah. Thank you.
Okay, we have to switch to the next talk, but we still have a chance. Thank you very much.
Thank you.
Talk, I guess, will be presented by Peter Hadavi. We still have the same talk from the same group, unless I'm wrong, because I see some common authors. So if you still haven't get a chance to ask your question about this interesting simulation environment, you still have for the second talk.
This is for, which is forward? Okay. Okay, great. Good afternoon, everyone. This is primarily the work of my PhD student, Myatsu Yin, and it's done in collaboration with Siri Won, who is our domain expert. She's an endodontic surgeon, and Patanapon, who built the simulator that we're using. So I'm going to be talking about, Nanamon just gave a talk on teaching of decision-making skills, and she said that's 75% of the important events in surgery. So I'm going to talk about the 25%. But 25% is still a lot of it, right? So I'm going to talk about teaching of psychomotor or physical skills. And as she mentioned, the mainstream approach in teaching dental surgery is a kind of a master apprenticeship model. So students are carrying this out on patients in a clinic, and you see the endodontist, in fact, that Siri one there from the side, watching and giving instruction. And she mentioned a number of limitations of this model. There are also limitations that impact the teaching of physical skills. So one is just the scarcity of experts. So you'll have an expert who's going around to different rooms in the clinic, in the surgical clinic, and they'll spend maybe 10 minutes with one student, and then they go off, and another, perhaps half an hour later, they come back. And so there's a certain amount of practice that's happening without any supervision. There's also a lot of subjectivity in the evaluation. So there is assessment that goes on, but it's actually quite subjective. And I'll come back to this at the end of the talk and illustrate this with some of the results we have on evaluation. And also a lack of standardization in terms of assessment. Now there are quite a number of dental VR systems that have been developed to help to address some of these problems. There's like DentSim, which is a commercial product, Fosslin Simulator, which is another commercial product. But these fall a little bit short in the area of formative feedback. And so that's what we're looking at, is how to add formative feedback to simulators. So let me explain what I mean by formative feedback. So if we want to provide effective formative feedback, first of all, we have to assess the outcome of the procedure. And so in dental surgery, we need to do things like talk about what kind of errors occurred, where did the errors occur, how severe were the errors. Okay, that's the first piece. And then we need information about how the procedure was carried out. So data on what was the path of the tool, how much force was applied, what was the orientation, the angulation of the tool, how much time was taken. And then what you want to do is you want to put those both together. So you want to know where were the errors, how bad are they, and then you want to look at the procedure and identify what is it about the procedure that caused these errors. Okay? And then finally you want to communicate this to the student. And you can communicate in a number of ways. I mean, you could provide a textual kind of communication. You can communicate graphically or visually. You could communicate this using videos. For example, you can show a video of the student carrying out the procedure and an expert at the same stage. And you can even communicate haptically, right? For example, if you want to talk about force, tell somebody how much force should you use. You use too much force at this stage of the procedure. Probably the best way to do that is physically through haptics. Let them feel how much force they used, what the right amount is. Okay, so in this talk, I'm focusing on the assessment of outcome, or the first component of this. So let me tell you a little bit about our simulator. Our simulator, you see a picture of it over there. It has two haptic devices. One controls the dental drill, one controls the mirror. We have a model of a patient's tooth, and this is created by doing a micro CT scan. We then do tissue segmentation on that scan to identify the different tissue types, because a tooth does have, has enamel, dentine, pulp. Intensities are also translated into tissue densities, so you get the proper haptic rendering. And then and this is all represented using an occupancy map, so basically a cube where each voxel has tissue type plus density value. And then the simulator records kinematic variables, tooth path, force or pressure, angulation. Okay, so how do we do the outcome scoring? So this is also focusing right now on root canal treatment. And what we're looking at here is the process of access opening. So the objective in access opening is to create an unobstructed opening from the top of the tooth to the root canals without removing an excess of tooth mass, right? So you want it to be just the right size, not too big, not too small. So how do we score this? Well, we have some templates which we automatically generate. So we have the optimal template, a kind of a maximum and a minimum, and this is sort of how dentists work. So we came up with this talking to the expert. And then there are scores associated with the maximum and minimum, and then of course there's a score associated, for example, with perforating the tooth, which is that the drill goes from the inside all the way out of the surface. And what we did initially is we came up with linear weights for the weights between the templates and the optimal and the template and the exterior. And it turned out that actually worked not well at all, okay? So once we came up with this sort of linear interpolation, it didn't correspond to the way dentists worked. And so then we went back and we looked at the data and we looked at our scoring and we talked to our expert, and it turns out that dentists actually score things in a very nonlinear fashion, assigning significantly higher weight to larger errors than to small errors. So for example, a tooth surface that has a lot of small errors would be scored a lot higher than a tooth surface that has one very major error on it. Okay, so you have to have a kind of a nonlinear scoring function. And so then what we do is we score all the voxels in the results. And of course, you don't want to communicate in terms of that kind of a detailed information. So then we translate that into a language that dentists are accustomed to. So they communicate scores in terms of the four walls of the tooth as well as the floor of the pulp chamber. And that's basically averaging. And then you come up with an overall score for the tooth, okay? So then we wanted to know how well this works, of course. And so in the evaluation, we wanted to look at two things. One was the degree of agreement between our automated outcome scoring and the human expert surgeons. But also we wanted to control for perception. So it's possible that the two would disagree just because our system has complete access to the tooth. I mean, doesn't have to perceive it, right? But the surgeon has to actually look at it and may not be able to see everything quite so clearly. So we wanted to look at what role does perception play as well. And so we worked with 3 endodontist raters. We had 15 outcome samples with a variety of different kinds of errors. And we ran 3 experiments providing different amounts of information. And then we looked at concordance correlation, which I think is the right way to look at this inter-rater agreement. So these are the 3 experiments. So one, we showed the raters what they would normally see, so just a 3D rendering of the tooth. The second, we provided some cross-sectional information, so a little bit more information than they would normally have. And the third one, we actually gave them the information from our automated scoring, so with a color coding showing where the errors are, what kind, if it's over-drilling, under-drilling, and severities, okay? And so our findings were, interestingly, first of all, the human raters didn't all agree. In fact, here we had 3. 2 of them agreed pretty well. One of them did not agree well at all with the other 2. And so this sort of points to the subjective nature of the assessment and also sort of the lack of standards. In fact, one of our dentists was trained at a different school, and that's part of it. And they also just sort of were tougher in their scoring. So we took the two who did agree with one another, and we looked at we focused on the agreement between their scores and our system, and the agreement is quite good. It's as good as the agreement between the 2 experts. So almost all values above 0.7 and many above 0.9. The other thing is we didn't see any effect of the information. So that says that the disagreements were fundamentally disagreements in judgment, not due to perception. Okay. By the way, we have, in the meantime, now expanded the number of experts. So we've run this now with 5 experts, and the results are the same. So basically, we're coming up with consistent results, right? And we knew 3 wasn't very much, but it's tough to get time of these people, right? These are busy people. So where are we going with this? Well, we're now working on the part where we correlate the procedure outcomes with the procedure. And this is basically a credit assignment problem, okay? And you see a little graph down there that shows errors over time. And what's interesting is that actually you can localize and space the error, but in the procedure it may have actually occurred, or the actions responsible may be in several parts of the procedure. And the other thing we're now looking at is different modalities for the feedback. So that's where we are and where we're going. Thanks very much.
We have maybe one very short question, and then we have to go. And please, third speaker already should come and set up. Well, the speaker is setting up. Last question. Oh, only question. First question too. All right. Well. Oh. Interesting. Thank you very much. Okay. Okay, now we have 2 long talks left. First talk is going to be about educational video, presented by Kuldeep Yadav. And the title is Visic Anchor Points Based Nonlinear Navigation and Summarization of Educational Videos. Ooh.
Okay. Hello, everyone. My name is Kuldeep Yadav. The title of my talk, as Peter said, is VISIC. I come from Xerox Center at India. So, I mean, if you look at videos, right? So, typically, if you look at textbooks, humans are pretty adept in navigating through textbooks. So, they frequently use table of content, maybe table of tables, table of figures, and they're pretty adept to navigating non-linearly through these documents. But what about videos? And the recent studies have found out that humans are actually, or the students on the MOOC platforms, navigate through videos also non-linearly. For instance, certificate earning students on EDX were spending only 4.4 minutes of their time on a 12 to 15 minute videos. They were doing a lot of non-linear navigation. I mean, on an average, if you look at 22% of the MOOC students were skipping content, and they were certificate earning students, so you can be rest assured that they were motivated for the content. There was another phenomenon where a lot of students were going back to the videos right when they were doing some assignments or problem solving. So, as well as these studies have found out that there is typically a point of interest every 2 minutes in a video. So, and these point of interest being that they are every 2 minutes is likely to be different for each user who is browsing through the video. So what do we have right now? So current MOOC platforms provide this nice interface where you can scrub through the timeline just like YouTube provides, as well as a essential time script which is time aligned along with the video. So you can click or search through that transcript and you can navigate to that point where something is written or something is talked about. But how about these scenarios? For instance, Alice is a student who is taking a MOOC course on computer networking, and she recently learned about a protocol called TCP. And while solving some kind of assignments, she had to revisit that video to see how TCP structure looks like. What are the different layers, how these different layers have bits spread out into them. So she wants to quickly reach out to that point. The only option that she has is to kind of scrub the timeline of the video to reach to that point. Consider a second scenario where Bob is an instructor who is looking for a right video of a heap sort to stream that in his classroom. So he wants to teach heap sort using a video in his classroom. And if he searches heap sort on any video search platform, he gets these different set of videos from different set of providers. Each video is a 50 minutes of length or maybe 20 minutes of length. He has to go through each of every video to find out which makes sense. He has a specific query where he wants to only select videos which probably has heap sort, describes heap sort with a flow chart or maybe a pseudocode into it. So can we satisfy these set of queries with the current set of platform? Probably not. Look at our IUI video streams maybe. So the one session stream is maybe 1.5 hours. So, and if you have to locate your paper, a day back I had to locate my demo presentation which lasted like 30 seconds. So it took me some time. So again, these are the videos because video itself traditionally has been a very linear way of navigation. So how we can assist a non-linear navigation or how we can bring a non-linear navigation system with respect to educational videos. That's our problem statement. And probably this does not help. So the current solution does not help to the scenarios that I kind of presented to you. So what we do? So to solve this problem, we analyze video content to automatically generate a multifaceted video index. These index consist of two different parts. So one is a concept flow. So we analyze audio and video content to find table of content as well as topic duration. So what is the so what are the concepts which has been discussed from in where in the video, and for how much time to which time, starting and ending time of those concepts. This work is already published, so this work was in Asia Multimedia this year. What I will be talking about here is that extraction of visual anchor points. So the second thing is not the textual kind of flow, but the visual. What is the visual information is embedded in that video? Can I see how many diagrams are there and whether those diagrams are located where in the video? Or same thing goes for the equations. So you have a Newton's law video. Can you support the equations where there is an equation in the video? And that is where our problem is. There are a few research challenges that we need to solve to kind of solve the second problem of localizing as well as classifying those visual anchor points. So we want to localize where there is a visual anchor point in a video. And the second thing is that you want to classify into one of the 6 different categories that I just demonstrated to you. So first challenge is the visual anchor points can take several different forms in a video. For instance, a table could be a 2 by 1 column table, or it could be 4 into 5 table. Diagrams across the videos could be different. I mean, there could be small architecture diagram to a more complex diagram to a different video. There is a heterogeneity in video production style. So for instance, there are some diagrams which might be hand-drawn, like the Khan Academy style, where there are some videos in Coursera or EDX which uses slides, and there might be much more formatted diagram there. Or there are even some videos which are blackboard captured. So if you look at in an Indian initiative called NPTEL, all the videos are classroom captured, where the resolution is so low that you can't even see the blackboard. Third thing is a lack of label data, because if you need to localize or classify, if you have to train a model, you need a label data to train that model. So how do you get this label data which says that which anchor point belongs to which? I mean, you need to say that, okay, this is a flowchart, this is a diagram, this is the equation. So you need that kind of label data. And then again, there's a high computation complexity that you find with all the video processing tasks, so there's nothing new in that. So that is what we do. So we have built this video processing pipeline, so where you can input any educational video. We extract frames from that video. After extracting frame, for every frame, we do slide versus content segmentation. What it essentially does is it tries to find where there is a textual or where there is a visual content in the slide. So it tries to segment the region which are visual heavy versus the textual heavy regions. The next step that we do, which is an in parallel step, is that we go to web. We find out the training data for each of these anchor points. So each of these anchor point means diagram, figure, equations, and all of those anchor points. We get a lot of training data to train our deep neural network model, which once we classify that there's a visual element in the slide, we pass it through our classification engine to tell, okay, which anchor point category does it belong to, which gives us the essentially the classification of those anchor points, and those anchor points location as well as the classification can be used for video navigation. So these are some of the snapshots that I kind of have, which just says that what kind of categories that it has. So for instance, these are the charts that we had. There were different kind of diagrams. So you see the heterogeneity, the make of these diagrams or these figures were totally different, which makes this problem very interesting. As well as the equations, it could be just one equation or a full slide full of equations. Same thing goes for the code blocks. Many times these slide-based videos have codes embedded into them, so you want to localize as well as classify them. Then there's a flowchart and tables. These are the 6 different anchor points that I talked earlier. So how did we perform? So the total number of images that we could get it from all these search engines were nearly 10,000 images, and we used multiple search engines to kind of. So one thing that this sold us is that we don't need to manual the label. We didn't need to manually label the data. So we didn't. All the data that we could download from these search engines kind of were self-sufficient in terms of training the system that how a table looks like, or how a diagram looks like, how a flowchart looks like. And this is the classification accuracy that we got. So our deep neural network based classification system could give us a average classification accuracy of nearly 86%. So it was confusing in some diagrams versus flowchart, which are nearly 14% or something. Probably we can enhance that accuracy in a future work, but right now it gives pretty good accuracy, which is self-sufficient for navigation system. So now the question arises that how we use this anchor points knowledge for the nonlinear video navigation. So what we do is, given a video, we extract table of topics that I described. So on the left-hand side, you see a table of topics that were automatically extracted. Then there's a 2D timeline which is presented just below the video, which just shows the location of different anchor points, as well as their category, whether that anchor point belongs to a diagram, or a table, or equation, or a code snippet. As well as what we could do is, since we could localize as well as classify these anchor points, we can extract from them from the slides, and we stack them as a jigsaw puzzle, which is a good summarization of all the visual entities in a video, and put it there as an annotation on the video. So if you click on any of these annotation, you can directly navigate to the point where that figure or diagram has been discussed. So if you click on any of the topics, so for instance, you clicked on Internet Reference Model, the 2D timeline shows the coverage from where to where that topic has been discussed, as well as what are the different visual anchor points embedded into that topic. So which is D and T that you see, diagram and table. So we did a user study to find out how did we fare with the traditional scrubbing, timeline scrubbing, as well as the transcript-based interface, where we identified 18 participants. All of them were registered into MOOC. All of them had a basic familiarity of educational videos. In fact, 17 of them were actually taking MOOC courses when they did the user study. We picked up 2 videos from a popular computer networking course. The video's duration was nearly 20 minutes. And we did a within participant study design where every participant tried both the interfaces on a different videos. And they had to solve 3 categories of different tasks. So we gave them tasks around visual search. So they have to locate some visual clue in the video, given our system and given the baseline interface. They have to take the multimodal search, where they have to locate a topic or a concept which has been discussed in the video, given a visual clue also. And the third was a problem-solving task. So this was primarily designed towards like in-video MOOC quizzes. So let's say when you take any MOOC course, you have to go through the in-video quizzes, which kind of pops up in between. So we kind of motivated some of the tasks on that side. And what we found out is that for all these 3 different categories of tasks, that navigation time saving that our new interface could get was statistically significant, and we performed better in all of these 3 different categories of tasks. So the knowledge or the multifaceted index that we kind of extracted from an educational video is very rich. And apart from navigation, it can be actually utilized for different kind of application scenarios. So some of these scenarios are as follows. So for instance, it can be utilized for multifaceted video search. So for instance, the search that you see on search engines, they're mostly metadata driven based on their description, based on their title. So if we have this detailed multifaceted index of educational videos, the search could be more directed towards the content of the video. For instance, you can probably search a video saying heap sort with a flowchart into it, and we will be able to give it to you. The second is navigational capabilities for quick video curation. So for instance, many times these people in developing countries or as well as in other classrooms want to utilize the high quality educational content in their classroom. And many times they want to only specifically remove some portion to kind of so that it does not conflict with the context of the class. For instance, if you have a probability video which discusses baseball as an example to kind of demonstrate it to the students, if you use that video in India, probably people don't understand baseball. So if you have to quickly replace that, annotate that baseball example, maybe let's say cricket. So how do you annotate those videos? And it requires heavily the navigation capabilities so that you can quickly locate and then probably replace that with a example which makes sense for the context. Third thing is targeted navigation in low bandwidth settings. So there are many studies which shows that if the video takes more than 10 seconds to load, nearly 40% of the people leave it at that point of time. So if you have more targeted navigation like these techniques, probably people are more likely to stick with the videos. So I think that's it. Thank you for the attention. This is my email ID.
We have 5 minutes for questions. I actually have first question. You have interesting progression of papers. So first you identify topics, and now you identify types of content. But there are a bunch of other people who work on similar things. For example, we've been working on social navigation. We show how much watching every segment obtained. And some other people worked on comments, for example. They place on video the marks where people commented. And each of that idea seems to be great. But if you like to place, the scrubber is not really very large. If you like to place marks where the table starting, where people making comments, where topics switching to each other, there's a lot of stuff on the scrubber. So we probably need to figuring out how we can, compromise and pick up the most essential one. Have you thought about it at the time?
Yeah. So I think this is a very, very valid problem of overloading the scrubber with a lot of these information, right? So, at least in Vizig interface, what we gave the capabilities to the participant was to hide and show. So based on the thing that they could show or hide the interface, if they don't like it or if they don't need it, they can probably hide the interface and they can watch the video in the isolation. So that is what we give. But yeah, it's a very valid problem given that when you try to combine these works coming from different things, one is the crowd work, which is like where people are commenting, bookmarking, and other things. And then there is a automated generation of work that, like the work that I just described, yeah.
Well, nobody's lining up, right? So I guess I have a chance to have another question. That's related one. So you already tried to switch it on and off, but everything has been off and on, right? There is no choice. For example, I don't care about tables. I really want to see pictures, but tables, I don't want to. Have you thought about that? Again, probably usability studies, because all of that idea is making interface more useful, but also more complex. And where is the sweet spot? I don't know.
Yeah. So for instance, this is again a very interesting question, and we have seen that in our user studies. For instance, when there was a multimodal search task that we presented to the user, there are two ways of navigating. One was through the topics, so you probably go to relevant topics and then try to search for a figure or a table there, right? Going from a textual to visual clue. But there are some people who actually went from visual to textual clue also. They search for a visual clue first and then probably saw, okay, which concept that this visual clue belongs to. So yeah, I don't have a clear answer on that, how to kind of enable that kind of navigation. But yeah, navigational patterns for each user is likely to be different. And if you can personalize the experience, that would be really great.
Thank you. So any more questions? All right, thank you very much. I can't believe that, but looks like we're getting to the very last talk of this conference. Guys, if you're really sorry about that, maybe we should ask the conference chair to get more talks, like 2-3 more talks. Maybe we can scrap something. Meanwhile, this talk is really last. We're going to talk about analytical talk. Talk about analytical, no, not talk. Analytical link.
Yes.
Guys, I just give up reading the titles. It's Bo Kang, and he will tell about his title.
Hi, everybody. My name is Bo. I'm coming from the University of Central Florida. Right now, I'm a PhD student. Right now, I'm talking about our work in the analytical ink and interact learning environment for math word problem solving. So in compared to the previous the presentation, I want you to just move from the microscopy to the microscopy work, because I'm really focused on the tiny stuff that I want to investigate. So today for the presentation, I will separate into 3 parts. In the first part, I'll tell you my motivation, why I'm doing this, the problem, the challenge. The second part, I'll dive into the deep technical details. And in the third part, I'll talk about our evaluation and what we find from the study. Okay, so the idea is simple. If you look at these 2 problems right now, like from the high school, the K-12 the education, you notice that in the left side, that's the state-of-the-art geometric theorem proving problems. And however, in the right side, all the problem contain the same concept as a midpoint. However, This problem actually really want to investigate if the student understand the quantitative information from this problem itself. Okay, so what I argue that would be the core difference between these two math geometry problems will be the left side will be focused on the qualitative, and on the right side is more focused on the quantitative. We really need to thanks for Descartes, to bring this great ideas, which boosting all our current science, everything we build right now. But then the question becomes, how could we let students in the high school to perceive such a great, important understanding? So in order to let them to continue to learn the advanced science like calculus, linear algebra, or all the different analytical the topics. So the first question that I ask myself will be, how could I build an intelligent tutor system to help students to understand the analytical geometry math problem and solve them and provide the scaffolding explanations. The complexities for solving such problem will be that the system need to or the user of the system need to using both the spatial reasoning, such as the diagrams, and the sequential reasoning using algebra skill in an iterative method. Actually, in the educational psychology, some researcher has already been proved in the fractional tutor that these two skills need to be developed in the iterative method. So I'm kind of like using this kind of evidence to further to build in the analytical geometry this knowledge domain. Okay, so the challenge will be, first one is how could we represent the quantitative information from analytical geometry problems. So actually this is the, this part is more relevant to the computational semantic work in the natural language processing side. The second challenge that I need to solve will be how could we further perform the quantitative reasoning based on the semantic representation that we develop. In this part, it's more about how to plan to solve the problem and also how to using the constraint solving based on the incomplete the input data. The third challenge will be how could we generate the context-sensitive tutoring scaffolds for the problems. For this part of work, which will be the corresponding related work will be more from the program synthesis community, which is the inverse of the natural language processing the research. They try to generate instead of recognition. The fourth challenge, we're moving from machinery to more human-oriented way, and the question will be how could we further analyze user input and give them adaptive scaffolds feedbacks. In this field, of course, in a lot of intelligent tutor system researchers do a lot of work on the algebra tutor or geometry tutor. However, what I did currently is trying to just combine these two, and in order to let students perceive the more critical important concept of analytical geometry. Lastly, is more of our field will be how could we let students to interact with the tutor engine as naturally as possible. So I will try to tell you how we design our user interface using the evidence that we used. First of all, the problem representations. If you see in the right side, the problem itself, actually there are a lot of quantitative information embedded in the natural language narratives. We're using the language model to define a domain-specific language, geometric language. In this level, we define three different categories of the syntax. One is knowledge entity, which map to a point, line, circle, so forth. And the second category will be knowledge attributes, such as, like, say, y-coordinate of a point or the slope of a line. The third category will be the knowledge relation, like, say, perpendicular between two lines and parallel of two lines. Okay, using these syntax blocks, we can just further build the semantic level to represent the math problems. We just using the direct cyclic graph to represent it, like in the right side of that graph, which is built. Currently, actually, in the natural language processing community, they do a lot of active research on the semantic parsing in order to generate such a DAG based on without labeling the input. However, for my scope, we just directly annotate the corresponding data, corresponding input, corresponding knowledge, and do the downstream the work that we need to focus. Okay, the second question that we need to ask, it will be based on the semantic that we developed, how we further do the quantitative reasoning. there will be three, I want to tell you the different scenario of the reasoning. First scenario will be forward reasoning. Like the first question that I present here, it will be giving you 2 points how to find the distance. If you compare to the second one, which is the back reasoning scenario, you notice that we give you the distance information or the value, quantitative values. Then we need to do the back reasoning in order to find the corresponding v values from backward manner. The third scenario will be more complex from the computational perspective. Will be if the problem itself have more concept embedded inside. So maybe the recursion will have been executed in order to do certain computations. So that's the three scenarios. Okay, in order to solve this problem, we just mapping how we do the cognitive reasoning into the corresponding high-level pipeline or algorithms. We first do the syntax match, pattern match, to generate the corresponding geometric concepts. And in the second step, which is most important, is do the constraint checking to make sure the current input tag is if there's any kind of relation exists upon the DAG, and see if the relation is there, then we update the DAG and further do the iteration. For certain cases, because new input knowledge can affect the different kind of nodes on the DAG, so the propagation should be executed in the step 4. Okay, during this the quantitative reasoning side, the scaffold generation will be executed as well. Executing the solving procedure will fire a lot of logic rules. Each logic rule maps to a scaffold step, which track the 2 status before and after the rule is executed. Also, the rule is applied rule and the meta rule. In our current system, we modeled different type of rules, such as arithmetic, algebraic, geometric pattern match rules, and verification, and so forth. A meta rule is just a context-free version of the applied rule. Okay, building upon the machinery like the representation, solving, and also the scaffolds generation, we want to answer the fourth question that we need to tackle, that is how to verify, check users' inputs based on the machinery, the representations. From the previously generated scaffolding trace, it actually is a linear sequence of geometric scaffoldings, where each one can contain a linear sequence of algebra scaffoldings. How to understand they will be easy is really straightforward. Imagine when you manipulate different kind of geometric concepts, you need to perform certain logic or the algebraic equation manipulations in your mind. So that's how the outer scope will mapping for all your geometric concept, the derivation, and in the inner scope, it all mapping to your logic side, how you perform the certain actions on the arithmetic algebra level. Based on this scaffolds, based on this scaffold graph, we do the match and verification algorithms to check users' answers in a deterministic way. First of all, we just see if the user input can match any trace step on the scaffolds graph. If the match is found, it means that the user are on the correct track. However, if the user input is not correct, it doesn't mean actually his or her solving is wrong, because he or she might using a different solution path towards the same answer. So what we did is we put that user input into the semantic DAG and let the semantic DAG to perform certain propagation and generate a scaffold trace. And then we compare the final answer from the scaffolding trace with the existing scaffolding trace graph, the answer. And if the answer is matched, it means students are on the correct track towards a solution. Otherwise, we just think that they will be wrong. In our current scenario for the scaffolds adaptation, we just using a status flag to track the current status in the scaffold tracing graph. So no matter if the student's input is correct or wrong, the pointer will be updated and to track how their cognitive thinking locate on. Okay, so for the fifth question, currently this is our proof concept, the user interface. On the top of the UI, that is the problem narrative region, and on the bottom side, that is the two working canvas, or we can say a working tool, the working memories. The first interaction on the UI will be we try to let people to really quickly to acquire certain knowledge before they do the problem solving. So we do some keyword highlighting based on the semantics that we annotate before. However, the visual cue is not sufficient to help people to acquire certain knowledge before they did the real problem solving. So what we do is that we let students to can interact or drag or manipulate certain key concepts from the given language, the problem narratives. Okay, so the corresponding will be, so I give you an example will be, if the user can drag, for instance, if she right now is solving this problem, she can just dragging the corresponding point on there. If she's dragging, like say, B, this point onto the geometry side, it cannot be dragged because it's not a concrete point. What he can do, it will be, he need to drag onto the algebra side. Then the student will think, oh, what is the answer of V? So then what he should drag will be, oh, C, drag a number of V. Then the value V, then the system will give the student certain kind of the scaffolds towards the solving, like in the, but though the scaffolds contain the concept distance, but she doesn't might know the real more detailed information of constants. So what she can do is that she continue drag the certain concept word from the problem and see the more detailed explanation of corresponding concept in order to further in order to further start to do the problem solving. And the besides the dragging in our tool working memory or tool working canvas, we support purely the sketch-based the user interface because we think this mimic how students do the math problem solving, how they do the logical reasoning side. In terms of the reasoning, we just simply simulate using a pen gesture question mark to simulate how their cognitive reasoning in order to communicate with the backend, the tutor engine. Okay, for our preliminary evaluation, in the our backend semantic solving, currently we have modeled 15 concepts and we annotate 30 problems. The way to evaluate is we hire 2 human tutors and we let them to grade this 30 problems separately, and they both agree that the corresponding solution is correct. In terms of tutoring and the user interaction side, we want to evaluate 3 independent variables. One is tutoring performance, one is the specifically UI keyword highlighting and dragging. The third one is overall usability. And actually right now our experimental design will be, we try to evaluate the independent 2 as the using a repeated measure design, and we evaluate tutoring performance and the whole user overall usability in both conditions at the same. And we recruited 10 participants in the first as a freshman in our university, and then they solved the 10 problems with the keyboard highlighting and dragging, and other 10 without it. Everything is counterbalanced and randomly assigned. Okay, from the evaluation, what we found will be for the tutoring the effect. Participants both use the system to check their answers and also do to ask for the next steps during their problem solving. And participants made the error rectification once during the study session. Here, the metric, the error rectification is calculated by the first step the user draw is required as a wrong, and the second time when he modify or write a new equation, that is correct. So we count as one error rectification. For the UI highlighting and dragging this interaction, participants made less queries and also made less error rectification. From our observation, because when you're dragging the concept words, it certainly can tell you more detailed information, which helps students to get avoid to certain problems and also make less errors. In the overall usability, students both believe that the dual canvas effect can help them to conduct such problem solving. The log file analysis, we found out that they definitely using the both canvas to input. Participants felt it was effective to use the pen and gesture as the input and the query method, which mimic how they're using the pen to do the problem solving in their pen, like their pen paper. Overall, participants were satisfied with the current proof of concept. Right now, the interaction side, if you try, you notice that there are still some errors on the recognition, which still intervene the users' their performance, which we need to further improve. But most importantly, is a scaffold adaptation. Though the system right now show the meta scaffold or scaffolds during the problem solving or the explanation, however, students don't think that is kind of useful because of several reasons, like say prediction accuracy or repeated scaffold explanation. Okay, the conclusion is analytical ink is an interactive tutoring system towards analytical geometry to facilitate the quantitative reasoning. Semantic graph representation make the connection between algebra reasoning and the geometric concept reasoning. The system is useful in terms of interaction technique user experience. And we shared all the source code in both the back end and front end, and the demos here. Okay, that's it. Yeah, thank you.
Okay, questions? Oh, it looks like we're wearing out. I have to ask a question as a chair. I actually have a question. So there, you introduced quite a lot of novel things in the system, and the part of the novelty has been related not with your semantical part, but the importance to support interface based on handwriting. Do you think that is really extra value or comparable to, for example, structured interface from Carnegie Mellon algebra tutors, which you cite in your paper? Do you think it was worth fighting for extra complexity?
Okay, yeah, that's a good question. As a matter of fact, if you notice that currently the geometry side, we are doing currently do an interaction comparison study between the structure versus sketch. However, in the algebra side, people can do the input has been already been proved that is more taking more effect towards the learning from another researcher per researcher. That's why we keep the algebra side as the more natural, more like this, more natural and more interactive as possible, yes. So in other words, we are continuously try to proving the interaction effect, and if that interaction effect can affect the learning effect, that's what we are currently doing based on this current proof concept system.
All right, but I noticed that you actually get two at least mistakes in recognition.
Yeah, that's why I'm saying like, yeah, for instance, right. Exactly.
Okay, folks, any more questions? Then I'm pleased to report, well, first of all, let's thank the speaker. All right, yeah. Thank you very much. It's tough to be last speaker, but the work was done very well. And then with that, I guess I'm closing the session and passing the baton to the chair.
Thank you very much, Peter. All right. So we are now done with the paper sessions. Yeah, is Joel here? You want to come up here? So I want to thank all of you for attending. This is, of course, just the end of the paper sessions. The conference is not over yet because we do have several events going on tomorrow. We have the free tutorial that Bart is giving. There's Bart over there on evaluating intelligent user interfaces with user experiments. So definitely, if you are here tomorrow, go check that out. It's about a half day. It ends just around lunch, I believe. So definitely go check that out. There are 2 workshops. I'm sure some of you are here to go to the workshops. And also the student consortium is going on tomorrow as well. For the people who are staying, nothing happens in this room tomorrow, so you don't need to come over here. The workshops are in the Palm rooms. This is all in the conference program. The student consortium is in Azalea, and the tutorial is in Maple. Azalea and Maple are in the building kind of across the road next to the stone building. So if you're looking for those, there will be student volunteers around to guide you. So hopefully that will help with finding wherever everything is going. I wanted to give a quick note about the live stream videos. Since you're here, you probably have not paid much attention to the live stream, but for the moment, those are still up on YouTube, publicly available. We'll probably make those private in the next couple days while we figure out all of the technical and legal situations behind making them available more long term. But so if you want to check out, if you want to rewatch a talk that you really enjoyed, or catch a talk that you missed because you were having too much fun during the coffee break, you can go check that out. All right, I want to thank a bunch of people, especially our sponsors: ACM, SIG-Chi, SIG-AI, and AAAI, and also, yes, let's applaud them. Also, our corporate supporters, our gold supporter, Microsoft. Our silver supporters, Google and IBM. And our bronze supporter, Tableau. Of course, it takes a lot of people to organize a conference like this, and I'd really like to thank all of our organizing committee members, especially our paper chairs. Massimo and Christina just left, so let's thank them, first of all. And then the chairs for demos and posters for workshops, our student volunteer chairs, proceedings chair. There's lots of them. I'm not going to say all their names right now, but you can go find them on the website, and if you see them walking around, please do thank them for us. Another very important thing for these sessions is, of course, the program committee who reviewed all the papers and wrote meta reviews as well. I don't know, anyone in the room who's on the program committee, maybe you can stand up, or if you reviewed. I guess none of them decided to come to the conference after they saw the papers. Anyway, let's thank them. And I also really especially want to thank all the student volunteers for both wearing the green shirt that we made you wear and for all the work you did during the conference. That was really great. I think very important. And then one final little shout out to David, who helped us make the live stream work, which that was super helpful. Thank you, David. All right, so that is pretty much it. What's going to happen now is a town hall meeting. So that's your opportunity to tell us, to tell next year's chairs what we did badly so they can do it better. And we have Antonio Kruger, the head of the steering committee, to lead you through that. I do want to also note that there is food and coffee out in the hall if you want to duck out and grab a little bit of something. Yeah, we're just going to go right into it, but feel free to go grab something out in the hall. And of course, if you're not interested in the town hall, you may, of course, depart. I think that's it. So thank you all very much again for coming.
Is there a chance that we can fire the project? Oh, perfect. Very good. I'm just starting this. So,
we don't need to live stream the town hall.
No, this is not necessary. Okay, so before we start with the town hall meeting, I would like to thank Jeff actually for putting all this together. Also Jalal and John, who basically brought a very